let's get started. Any questions on the project? Any questions on the project? Okay. All right. So then, looks like we only have 7 people in the class. One second. Yeah. Maybe we'll just wait for a minute and then we'll get started. In the meanwhile, so the derivation that we did yesterday, we got to a point where we were able to solve for the Q, the outflow, and the storage as a function of time. Right? So this is the equation that we derived, the one that you see over here. That's where we got to yesterday. So any questions on that? Okay, so maybe let me just note down the equation. All right. I can explain the procedure once again, just in case there's any clarity that's required. Okay, what's the time? Still we only have 7 people in the class and it's time. Okay, so we'll just let people join in as they come. So very quick recap of what we did yesterday. We were looking at this idea of routing a flood through a reservoir, and we wanted to understand how to do it using this method, what we call the level pool routing method, right? So in this level pool routing method, what is known is the inflow coming into the reservoir. I as a function of t is known. The outflow out of the reservoir at time t equal to 0 is known. The storage at time t equal to 0 is known. Okay, so these 3 pieces of information are known. What we also know is the storage characteristics of the reservoir, right? So here I have storage versus H, right? So depending on the water level in the reservoir, we know what the storage term will be, right? So if the water level is at a certain height, then that means the storage is so and so and so on. So I have a curve that represents the storage as a function of the water level in the reservoir. Similarly, I have the outflow from the reservoir as a function of H, right? So depending on what the head is, you'll have different levels of outflow from the reservoir. So we have S as a function of H and Q as a function of H. So these 2 pieces of information are available to us. Once we have these 2 pieces of information, I combine these 2 pieces of information and compute this term over here, 2S by delta T plus Q, and plot that as a function of Q, right? Because Q and S, both of them are functions of H. So for different values of H, I can compute what this value will be, assuming that I know what the delta T is, right? So if I'm looking at a particular problem, that problem will have its own delta T, right? So depending on the problem, you can compute this x-axis, which is 2S by delta T plus Q, and then I have Q on the y-axis. So I have a curve that represents these 2. I mean, of course, you can also plot it Q on the x-axis and that 2S by delta T plus Q on the y-axis. That's not a problem. The objective is not, the point is not whether it is on the x or y-axis. The point is that we have a curve that represents Q versus 2S by delta T plus Q. Now the question is, why do we need this? So for that, we have to just look back into the derivation that we did. Maybe I'll just spend a little bit of time on that, right? So we have, for any hydrologic system, we have the equation ds by dt equal to I of t minus q of t, right? So if I write this as some kind of a, in terms of a different scheme, right? So ds by dt is simply s at j plus 1 minus s of j, and then the dt I've taken it to the other side, so I get ij plus 1 by 2 times delta t. We just worked out how we did that, right? Similarly, qj plus 1 divided by 2 into delta t. That's the area under the curve on the outflow hydrograph. So then what I did was I just assembled the unknown terms on one side. So I get this term on the left hand side, which is all the unknowns. Storage at j plus 1 time step is not known. The outflow at j plus 1 time step is not known. So this entire left hand side is unknown. On the right hand side, I have accumulated all those terms in that equation which are known to me, right? I know ij, I also know ij plus 1. So I club them together on the right hand side. I also know storage at time step j and the outflow at time step j. Correct. So what I've done is I've just separated these terms out in such a way that all the unknowns are on the left hand side and all the knowns are on the right hand side. So naturally, since I know all these terms on the on the right hand side, I just put in those numbers and I compute this left hand side, which is a combination of the storage term and the outflow term. Correct. So right, so I obtained this value for 2s by delta t plus q at the j plus 1th time step. Right. So that is where this curve comes in, the next figure that I had shown, right? So I have 2s by delta t plus q at j plus 1th time step. Since this curve gives you q as a function of this term 2s by delta t plus q, you can very easily find out what the q corresponding to this particular value of 2s by delta t plus q is, right? So since I have solved for this term over here, I simply look up on this curve for what value of q do I get this value of 2s by delta t plus q, right? So that gives me q, and once I know q, I can solve for s, right? So this curve will give me qj plus 1, right? So the first thing we do is solve for qj plus 1 using this curve. Once I know qj plus 1, I can solve for sj plus 1, right? Because I know the summation of these two terms I know. And if I know qj plus 1, I can simply solve for sj plus 1. Okay. Any questions on this? Okay. So what we'll do now is we will look at a problem. And what I've done is I've set up this problem in Excel, but we'll just go through the problem statement here and then we will go into Excel and solve it. Okay. All right. So let's read the problem. A reservoir for detaining flood flows is 1 acre in horizontal area, has vertical sides, and has a 5-foot diameter reinforced concrete pipe as the outlet structure. Okay. The HQ relation for the outlet pipe is given, right? So this table that you see over here is the relationship between H and Q. Okay, HQ is given. Use the level pool routing method to calculate the reservoir outflow from the inflow hydrograph given. This is the inflow hydrograph, right? As a function of time, what is the inflow in this units that you see, CFS? CFS is simply cubic feet per second, right? Feet cube per second. All right. So this is something that you need to be aware of. CMS is meter cube per second. Typically, sometimes it's also written as CUM/S, cubic meters per second, right? This cubic feet per second is also sometimes referred to as Cusecs, CUSECS, right? Cubic feet per second is just as a short form, it's referred to as Cusecs. So in fact, if you read the newspapers, it will say 4 lakh Cusecs was released from the Sri Salem Dam and so on, right? Because of incoming flow, 4 lakh Cusecs was released, or 7 lakh Cusecs was released. So this is a term that you may see often. Just you need to be aware of what it means, right? All right. So this is the piece of information that's available to you. The HQ relationship is known. The inflow hydrograph is known. What you're asked to, let's look at the last statement. Assume that the reservoir is initially empty, right? So the storage at time t equal to 0 is known. The storage at time t equal to 0 is 0 because 0 cubic feet, because the reservoir is initially empty. The outflow naturally at time t equal to 0 will also be 0 feet cube per second, right? So we already know the S and Q values at time t equal to 0. The relationship between H and Q is given over here. This table gives you the relationship between H and Q. Now, what other information do we need to solve this problem? Is all the information required to solve this problem available to us? Let's just quickly go back to this previous figure and then see what we need, right? H versus Q is known. So this piece of information is already known. Ij and Ij plus 1 is known, no problem. Do we have this curve? we don't. We'll have to construct this. But what about storage versus height? Is that known? What about storage versus height? S versus H. Let's go back to the problem statement. Read the problem statement. A reservoir for detaining flood flows is 1 acre in horizontal area. So when I say horizontal area in plan view, so if let us say this is the reservoir, okay, in plan view, so this area is 1 acre, okay, has vertical slides. So if I draw a cross section of this reservoir, it will look like this. Okay, it's obviously exaggerated. All right. So this is my H. So can we not find out storage as a function of H? Because we know this area, this cross-sectional area is known. It's given to you, 1 acre or whatever it is. Okay. It has vertical sides. The reservoir has vertical sides. The sides are vertical, right? Which means the area does not change as a function of height. Let's suppose I have a reservoir that looks like this. Okay. Depending on the height, the area will also differ, right? So at different values of height, the cross-sectional area is changing. That's not the reservoir that we're talking about. We are talking about this kind of a reservoir, which has vertical sides and the area is given to you. Okay. So naturally from here, we can develop the H versus S relationship or S versus H relationship. HQ is known, HS is known, I at J and J plus 1 is known. You simply have to solve for Q at every time step. Okay, so is that clear what we are trying to do, what we are trying to accomplish? All right, so what I'll do is I'll go to Excel and let me show, I'm sharing this. Okay, my Excel file is okay. Are you able to see my Excel file?
Yes, sir.
Okay. So the problem statement is again mentioned over here. A reservoir for detaining flood flows is 1 acre in horizontal area, has vertical slides, and has a 5-foot diameter reinforced concrete pipe as the outlet structure. Okay, the HQ relationship is given. Use the level pool routing method to calculate the reservoir outflow from the inflow hydrograph given. Assume that the reservoir is initially empty. Okay, so here is my outflow HQ relationship, H versus Q, right? So this is given information. Whatever is over here is all given. Okay. What about storage for these values of H? Can I also find the storage? How would I do that? So here some information is given to you. 1 acre is 43,560 square feet, right? So how would I find out storage? Okay, looks like nobody is in the mood to talk today, so I'll have to call somebody. Nikhil?
Yes, sir.
Yeah, can you do
Area
this?
into height.
Area into height, right? So simple. Okay, so let me just go in here. And so what I've done is I've simply done exactly what he suggested. Thank you, Nikhil. Okay, I'll just change the color. I've already entered the numbers. I just put it in white font so that it's not visible before we solve it. Okay, so we have the so let's look at the equation over here. So the equation in this cell is area, which is over here. 1 acre is 43,560 square feet multiplied by A10, right? A10 is the height. So if height is 0, then naturally the storage is 0. And I'm sure you all know about using these dollar signs over here. If you want to copy the formula and you don't want the you want to refer to the same cell all the time, you put in this $D $8. So when I copy this formula down, it retains the same cell. Right? Are you aware of this? Have you guys have used Excel enough to know this?
No.
No. Okay. So this is a trick that you can use in Excel. Okay. So if I put $D $8, then I'll just show you. When I copy this formula to the next cell, Okay, so you notice the difference between the two cells. Are you able to see that the formula over here equal to $D $8 into A11? A11 is this cell, right? The previous cell was $D $8 into A10, right? So when I copy it from this cell to the next cell, automatically it knows that it has to use the height from this the next row, but it will not change the location of this original value, the area. In this case, it's the area, right? Sometimes you may want to change the row but not the column. Sometimes you may want to change the column but not the row. In this case, I don't want to change either the row or the column when I copy the formula, right? So this is just a trick that you use in Excel. Okay, so I'll just copy this formula all the way down. So I have a function of, right? And if you, I'll send this file to everybody so you'll all know how to use it and so on. Okay, it's not a big deal. And these are small tricks that you need to learn, when you're using Excel and so on. Most likely for the rest of your lives, rest of our lives, we are going to be using Microsoft Excel unless some other software comes up, right? Which seems unlikely to me, right? So it's a valuable trick to learn, and it's not all that difficult. Okay, so here I've computed storage as a function of h. Q as a function of h is already given to me. Then can I not compute 2s by delta t plus q? This term over here, 2s by delta t plus q, it's very easy to compute that, right? Because I know S and I know Q, I can simply compute this term. Okay, so let's see what I do over here. So I do 2 into C10. C10 is the storage divided by delta T. Delta T is 600 seconds. I've used 600 seconds because, why have I used 600 seconds? Can anybody see why I've done that? Delta T, I have used 600 seconds. The answer is right there in front of you. Anybody?
10 minutes.
Yeah. So you see the inflow hydrograph that is given to you is in time steps of 10 minutes, 0, 10, 20, 30, 40 in minutes, right? So therefore my delta T in this case, you can always use a smaller delta T if you want, but preferably, you should not use a delta T greater than the time step that is given to you in the problem, right? You may use something which is at a finer time step, but it won't make any difference. It won't make too much of a difference to your answers. Okay. So anyway, so now we've got 2s by delta t plus q. So 2 into s is over here divided by delta t 600 plus q. So now remember, we are developing this relationship between 2s by delta t plus q for the same value of h. I'm using the q and s for that corresponding value of h, right? So this C10 and B10 correspond to the values of q and s for a h of 0. I can't take q as 0 and s as some other number and compute 2s by delta t plus q. It has to be for that corresponding value of h, right? So that's what I've done. All right, so then I'll just this again. I can do the same thing. The same formula is copied all the way down. So these are the numbers. So this is my, so you see column B over here is q, column D for Delhi is 2s by delta t plus q. Now if you think about it, you have all the available all the information that you need to solve this problem, right? You need to know ij and ij plus 1, that is given to you. You need to know what was that, 2s j by delta t minus q j plus j, that you can find out because you already know the s and q at time step 0, right? S and q are 0 when time step at time t equal to 0, right? So we'll take it forward from there. Okay, so let us come to this side of the solution. Okay, so first thing we do is, for every time step I compute ij plus 1, right? So this is the inflow hydrograph that's given to you in this column h. So in the next column I'm going to compute ij plus 1. Okay, will it continue beyond time t equal to 150 minutes? It won't, right? Because at this time step ij plus 1 is not defined. Okay, so we don't need it. So we just stop at the inflow starts at time t equal to 0 and ends at time t equal to 150. Okay, so here I have in this column ij plus ij plus 1. What have I done? Let us look at the formula. ij plus ij plus 1, h10 plus h11. The next cell will be h10 h11 plus h12, 60 plus 120. Next one will be 120 plus 180, and so on. Okay, any questions so far with what we are doing? All right. Okay, so now we'll come to the next cell. So the next cell, what is the next cell? 2s by delta t minus q. This number has got to be calculated at which time interval? I realize that there may be some, let me do one thing. Let me quickly try some. Okay. Okay, this is my equation. Okay, you're able to see this equation? Are you able to see the equation?
Yes, sir.
Yeah.
Yes,
Okay.
sir.
So you see, ij plus ij plus 1 I have computed in column I. Oh, coincidentally, it's in column I. Okay. The next column is 2s by delta t minus q, which I need to know at time step j to be able to solve for time step j plus 1. Right? Everything on the right hand side is known, everything on the left hand side is unknown. Okay. So if I know these values at time step j, I can find out these values at time step j plus 1. Okay. So at time t equal to 0, the head was 0. So therefore, q and s were also 0. So that this cell becomes simply 2s by delta t minus q is 0. Okay. Is 2s by delta t plus q defined for time step j? The next column that you see over here, 2s by delta t plus q, you can write it. That is also 0 at time step 0. Right? What is the outflow at time t equal to 0? You already know this.
0.
0. Okay, so we'll just fill in this. I mean, these numbers don't have any meaning because we have not computed anything. Okay, so we have all these numbers. Now we go to time step j plus 1. Okay, so when I go to time step j plus 1, let us look at the formula in the next time step. So now this time step, I can only solve for it when I know everything from the previous time step. Do I have all the information required to solve it? Look at the formula here. 2s by delta t plus q, right? 2s by delta t plus q at the time step of j plus 1 equal to ij plus ij plus 1, which is this number over here, plus 2s by delta t minus q at time interval j, or at time step j. Right? So that's what this formula is. Right? So I compute this number from the previous time steps data. Right? This data was known, this was known, so I compute this number 2s by delta t plus q. Okay? Is that okay?
Yes, sir.
Okay. So now that I know 2s by delta t plus q, what should I do? I mean, sorry, I'll say 2s by delta t plus q at time step j plus 1. I know this term over here. I know this term at time step j plus 1. Okay, what should I do next?
Find QJ.
Find qj plus 1. Correct. But how do I do that?
Using hydrograph.
Not the hydrograph. Using the plot between,
Inter
interpolate between, see, so I have here in column B and D, I have 2s by delta t plus q as a function of q. Right? So this column D and column Q, what are they? It's a plot between 2s by delta t plus q and q. Right? So I know that at time step j plus 1, 2s by delta t plus q is 60, right? Which is somewhere between 0 and 75.6. Correct? So if 2s by delta t plus q is 60, then q must be somewhere between 0 and 3. Are you guys following? You understand what I'm doing over here?
Yes, sir.
Yeah. Thank you, Ajay. Others, if you're keeping quiet, I'm assuming you're all understanding everything. If there is anything that requires clarity, please stop. It might not be the easiest thing, right? I mean, because the equation is on the PowerPoint. I'm coming to Excel over here. It's a little bit confusing. See, usually in class I have the board and the screen, right, and the projector. So I would show the Excel computation on the screen, but the board is also there, so I can use the board. But now it's a little bit difficult, right? So that's why I've got the equation copied in here. It's the best we can do given the circumstances. Okay. So anyway, so
Sir,
yes.
sir, if I already know the discharge and the storage capacity, why am I calculating the discharge again? I mean,
No, you don't
I
know.
can
You don't know the discharge. You only know discharge as a function of h. You don't know discharge as a function of time.
okay.
Okay. So you see, if the water level in the reservoir is at a certain level, then you can measure the discharge and then say, oh, this is the relationship between h and discharge, right? But
Yes.
what I don't know is if a certain inflow is coming in, okay, it's going to impact the water level in the reservoir, which means it will impact the storage, and thereby it will impact the uh, outflow, right? But I don't know how it's going to change.
Mm.
See, this particular example, we have used this kind of a simple reservoir which has got an area that is not changing as a function of height. In reality, with a little bit of a change in the height, the storage may increase dramatically. But as soon as height changes, the outflow also changes, right? So therefore, you've always got to keep computing the outflow at every instant of time because the inflow is changing. When the inflow changes, the storage in the reservoir changes. When the storage changes, the height changes. When the height changes, the Q changes. So you always have to compute the consequence of whatever change is happening because of the inflow. So that is why when I'm solving for Qj plus 1 and Sj plus 1, I'm using Ij and Ij plus 1. Correct?
Okay.
So I know what the storage was and what the outflow was in the previous time step. In the new time step, to know what the outflow and storage will be, I need to know how much has come in since then. That's why this Ij plus 1 is also included in the equation. If you look at it from a physical point of view, right, I have Ij plus 1 also in the equation, which is accounting for how much is coming in. Only if I know how much is coming in, I'll know whether the water level will change, by how much it will change, whether the outflow will change, by how much it will change, and so on. Okay.
Yes, sir.
All right. So the the point I'm making is very simple. I know now that this term 2s by delta t plus q at this time step j plus 1 is 60. I've computed that using the previous time step. Once I know it is 60, I simply come here, I look at this table. Oh, when 2s by delta t plus q is 75.6, q will be 3 CFS. But here it's 60, so it must be little less than 3 CFS. How much less? The best thing we can do is to do a linear interpolation. So that's what we've done over here. Okay, so I'll not explain this linear interpolation. You guys know how to do it, right? So it's B10 plus B11 minus B10 into K11 minus E10, whatever it is. Okay, you figure out the mathematics. It's simple linear interpolation, right? I don't think I should explain this in more detail. So I've linearly interpolated between 0 and 3 and 0 and 75.6 for 60. For this column being equal to 60, linearly interpolation, by using linear interpolation, I have found out that Q will be 2.38. Okay. Okay. So now I have 2s by delta t plus q at j plus 1 time step and q at j plus 1 time step. What was my objective? Look at the problem statement. Use level pool routing method to calculate the reservoir outflow from the inflow hydrograph given. My objective is to find, just like I know the inflow hydrograph, I want to find out what the outflow hydrograph is. Okay, that is my objective. So far, I have done well. I already knew Qj. Now I have no Qj plus 1. Now I should go to the next time step. For the next time step, what information will I need? For the next time step, I will need, so next time step means I have to come over here and compute this number. Okay. For the next time step, I need to know what this 2s by delta t plus q is. For which, what do I need? I need to know ij plus 1, which will be the this cell, and 2s by delta t minus q at time step j. Okay. So now look at what happens over here. This 2s by delta t minus q. Now I have to compute it for the jth time step. Since I have moved to the j plus 1th time step, this row will become the jth time step, right? So just look at the formula over here. What is this formula? 2s by delta t minus q at the jth time step is simply 2s by delta t plus q minus 2 times q. You see this? You see this k11, which is 2s by delta t plus q minus 2 times q. Is this okay? You understand what is happening here?
Yes, sir.
How did I compute this term? I simply computed it as, once I finish this computation, it is no longer j plus 1. When I move to the next time step, this row becomes jth time step, right? So 2s by delta t minus q at the jth time step will simply be 2s by delta t plus q at the jth time step minus 2 times q at the jth time step. That's what this formula is. Right? I always use the current information to compute the terms, and whenever I want to go to the next time step, I have to use the appropriate formula. Okay, so I come here. So I've computed this 2s by delta t minus q at the jth time step. Remember, the jth time step is now 10 minutes. J plus 1 is 20 minutes. So I come to the j plus 1th time step. What is the formula? Very, very simple. It is ij plus 1, which is this cell I11, plus J11, which is 2s by delta t minus q at time step j. Okay. So that gives me number 235.24. Okay. So after I finish computing this, what do I do? After finishing this computation, after computing this 2s by delta t plus q at the j plus 1 time step, what do? I compute q at j plus 1 time step. So what do I have to do for that? I come back to this table and look at the value of 2s by delta t plus q. It is 235.24. So I come down this table. I see that it is just greater than this 234.8. Right? When q is 200, when this 2s by delta t plus q is 234.8, my discharge is 17 CFS, 17 cubic feet per second. Here I have this 235.24 is just a little bit greater than 234.8. So my Q should be just a little bit greater than 17 and less than 30 CFS, right? So then again, I come back here and I do the linear interpolation between 17 and 30 and 234.8 and 320.4, right? I implement that and I get the answer. So the answer over here will be 17.07. Okay. All right. So I've computed a couple of time steps. So I think you know how to go forward from here. You just keep repeating the same procedure. So let me just show you. So then I compute this thing at time step j by using 2s by delta t plus q minus 2 times q. Do that. I compute this. Then I go to the next time step, which will be ij plus 1 plus 2s by delta t minus q at jth time step. Right? I have that number over here. Then I go back into the table. I look at it. It's 501.11. It falls somewhere between these two numbers, 495 and 586. So again, I do linear interpolation there. Okay, 61.09 and so on. Okay, I'll not bore you with the remaining computations, but I'll just fill in the entire table. So I want you to notice. I didn't actually compute all of this. I just put in the numbers after that because there's no point in doing all those computations. This is a solved example from one of the textbooks. So I've just put in the numbers. I just solved the first few 3 or 4 time steps. just to show you how it's done. So the information is embedded in the Excel file. Okay, so when I upload this Excel file, you can use this and look at it to understand how the methodology works. Okay, so this over here is the outflow hydrograph. All right, any questions on this, on the procedure? Any questions on the procedure? All right, so now I want to show you a couple of things in this. Yeah, so this plot that you see over here, yeah, so this is the plot between 2s by delta t plus q and q. Okay, this is just to show you what it looks like. Okay, we didn't actually use this plot, but if you're doing it graphically, you could always interpolate between these 2 points when you compute this q value over here. Okay, but we've done it numerically, so therefore we don't need the plot. But imagine you have a plot like this available. You could always go in and linearly interpolate, graphically interpolate to find out what the value of q would be. Okay, so that is this chart. Now the other chart that would be interesting to look at is over here. I've kept it over here. Okay, unfortunately I've forgotten to add the x-axis labels and the y-axis labels, so excuse me for that. But let's just look at what these 2 plots are showing us. The blue curve that you see over here is the inflow hydrograph, and then this kind of orangish color that you see, that is the outflow hydrograph, right? So now, can anybody tell me what are the 2 features that you noticed from this from these 2 plots? Something that we spoke about in yesterday's class. There's 2 features that are noteworthy. What are they?
The peak of outflow has reduced.
Peak of the outflow has reduced. Okay, thank you, Aditya. Somebody else? Anything else that you noticed?
Time lag.
There's a time lag, right? Okay, so just in case I forget, I just want to insert the axis titles and so on. Okay, so on the x-axis I have time in minutes, and on the y-axis I have, what's on the y-axis? I can say discharge, and it's in cubic feet per second. Okay, maybe we can even add a legend. Okay, just say series 1, series 2 right now. That also, let me quickly change it. Edit. So it's inflow, and I hope you're all familiar with using Excel and so on, right? Okay, so now this is an acceptable graph. Okay, please make sure that whenever you produce a graph, you have the x-axis and the y-axis labeled, and if you have more than one plot on the graph, then you should have a legend which says what the different colors or the different symbols mean, right? So here I have inflow and outflow. So these are the 2 features that are noteworthy. One is that the peak, which used to be about 350 cubic feet per second, has now become smaller, which is somewhere around 270 or whatever. Okay, and then the time to peak, it used to be something like 60 minutes, and now the time to peak has become 80 minutes. Okay, so to that extent, the reservoir has been able to absorb the incoming flood and lower the peak and increase the time to the peak of the outflow on the outflow side. All right, any questions? Any questions at all? Okay, all right, so now let me go back to my PowerPoint. Are you able to see the PowerPoint? Oh, wait a second, I have to stop sharing the Excel and then start sharing the PowerPoint. Yeah, so is the PowerPoint visible now?
Yes, sir.
Okay, so we've solved this problem. We've obtained the outflow hydrograph using the level pool routing method. Okay, there's nothing fundamentally difficult about it. It's just intensive in terms of computations and so on. And especially if you have to do a long problem, doing it by hand would be something very painful. Okay, so that's the kind of the challenge in these kinds of problems. All right. Okay, so now let's move on to the next topic. So now, so far we were talking about routing of a flood through a reservoir, which basically absorbs the incoming flood, lowers the peak, and lets it out into the on the outflow side into a channel. Okay. So now, when I release that outflow discharge into a channel, okay, so you can understand that. See, if you remember correctly, you from the previous semester when we spoke about open channel flows, we spoke about the idea of uniform flow, right? And then we also spoke about gradually varying flow and so on. Now here, if you notice, this inflow hydrograph is changing as a function of time, okay? And naturally, the outflow hydrograph is also changing as a function of time, okay? So the objective is to try to look at the response of a river channel, okay, to this kind of an outflow hydrograph, which is coming in the form of a wave, right? There is the outflow discharge has a certain value. It increases as a function of time, and then again it decreases back and goes back to, let us say, the original value, right? So let us assume that I have a river. Okay, so let us say I have a river somewhere over here where the water is just flowing at some constant rate. Okay, then because of some rainfall event, there is a reservoir which is receiving some incoming flood. The reservoir handles that flood by lowering the peak and increasing the time and so on, and it releases out into this river. Now that flood of outflow hydrograph is going to come into this channel, okay, and it is going to pass down this channel in the form of, you can think of it like as if a flood wave is passing. Flood wave is passing, through the channel reach, or it's going past the channel. Okay, so now when I have this kind of a flood wave, my intention is to try to understand to what extent can the channel's own storage handle this kind of a passing flood wave, right? So now, if you let me just draw a cross section of a channel. So let's just imagine I have a channel like this. At some time t, I have some flow going through the channel at some water level. Okay. Now, when this flood comes in through this channel, naturally you will expect that the water level in the channel is going to change, and it's going to become something like this, maybe. Okay, depending on the extent, the magnitude of the flood, and depending on what kind of side slopes the channel has, it may rise up like this. If I have an even flatter channel, okay, I may see only a little bit of an increase in the depth. If I have a perfectly rectangular channel, right, I may see for the same level of discharge, I may see a much higher increase in water level, right? Because the cross-sectional area is not changing as a function of depth. So to accommodate the same flow, I may have to increase the water level by much more, right? So naturally, these three different cross-sections, I'm just kind of exaggerating. So this would be a kind of an idealized cross-section. This is a more gentle kind of slope, and this is the other extreme, where in fact my cross-sectional area is not changing as a function of time. Okay, so you can imagine that these different cross-sections would behave very differently given the same flood coming in, right? So now the objective is to try to understand. So I'll just erase this. The objective is to try to understand how much storage the channel itself can provide to an incoming flood, right? So depending on the nature of the flood, some of these floods, the channel by itself, by the very nature of the channel, it may be able to handle a flood, right? I mean, you've all experienced this in the last month or so, right? Depending on the channel, it may be able to handle the flood. Only in a certain cases, when the channel is unable to handle that flood, then that flood spills over and it becomes, and it kind of inundates the city, or it inundates the low-lying areas around that. But if the extent of if the magnitude of the flood is such that the channel by itself is able to accommodate that flood, right? So then the objective is to try to understand, the ability of the channel to accommodate this flood, which means the channel also has some kind of storage right? So the channel also has some ability to store water. Okay, so what we are going to do in this is to try to model the storage in the channel itself. Okay, we will try to understand how the storage in the model changes as a function of this incoming flood. Okay, that is the objective of this whole analysis. Okay, so when I say the storage in the channel, it is going to be modeled using a combination of what is called prism storage and wedge storage. Okay, so let me try to explain what these terms mean. This is something that probably you've not encountered before. Okay, we are going to we are going to simulate or model the storage in the channel as a combination of prism storage and wedge storage. Okay, wedge. You might have heard these terms used in other contexts, but you might not necessarily know what they mean in this context. So let me try to explain that. Okay. All right. So what I'm going to try to draw is a three-dimensional picture. So kindly bear with me if it isn't too good. Okay. So let me try my best. Okay. So imagine a channel reach. Okay. So, okay. Imagine that this is the reach of channel. When I say reach, I mean a certain portion of the channel. Okay. Some distance along the channel. Assume that the flow is happening from this cross section to this cross section along the channel. Okay, I'm not going to try to draw it very accurately in 3D, but just I hope you can imagine it. Okay, so let us imagine that initially before the flood comes in, the channel is flowing at some kind of a uniform flow condition. Okay, so it will have some depth over here. If it's uniform flow, then the depth here is the same as the depth at the previous cross section, assuming that the channel cross section is kind of the same. Okay. So now let me try to draw a line joining these two. Okay. This is where the three-dimensionality becomes a little bit challenging. Let me try it. Okay. So I hope you can understand what I'm trying to draw. Okay. So maybe I'll draw instead of drawing it in some kind of three-dimensional view, let me try a cross section. Okay. So let us say I have cross section 1 and cross section 2. Okay. This is the bottom of the channel, and assuming that its initial assuming that initially the flow is uniform, then I'll get something that looks like this. Now, naturally, when I'm showing it in a cross-section view, it looks like a rectangle, but in reality, it is it's some really struggling to draw what I have in mind. Okay, it's something that looks like this, extended in 3 dimensions. Right? Something that looks okay. Maybe this is a better one. So I have over here. No, it's not really a better one. Are you able to understand what I'm trying to say? That I'm just trying to imagine what this volume will look like. Okay, in the channel, right? Assume a uniform cross section. Then, if I just draw a kind of a three-dimensional object that that captures this volume, it will look something like this. It will have a cross-section area. If you look at this rectangle, if you look at this rectangle from this side, if you look at this rectangle from this side, for example, okay, if you look at it from this side, it will look like this. Okay, and it will just extend for this length. So this entire distance, it will have the same kind of shape and it will extend throughout this entire thing. Okay, so that portion of the storage, I'm calling it prism storage. It's like a prism, right? So you might have done your experiments in the physics lab where you have a light passing through a prism and so on. So imagine this kind of a shape which is just uniform cross section throughout and has some length. Okay, so I'm calling this some kind of a prism. Okay, so this storage I'm calling it the prism storage of the channel. Okay, then some inflow comes in into this channel. Okay, which is in the form of a flood. Okay, so what happens? What is the immediate response of the channel? So let us say there's an incoming flow. Okay, so this is the outgoing flow Q in this channel reach. So now see, although in the previous one I described I and Q as the inflow and outflow from the reservoir. Now this here in this channel reach, you have to think of the inflow as the incoming flood and Q as the outgoing flow at the other end of the channel reach. Okay, so an incoming flood comes into this reach. So what happens to the water level in the at the first cross section? What happens to the water level over here? When the flood comes in here, the water level here will naturally it will go up, right? Oops. It will go up something like this. Correct? Here the water level is still the same original level. Instantaneously, if you look at this entire reach, the water level here would have gone up because of this incoming flood, while here the water level is still remains at the same level. So then if I look at the cross section profile, okay, it will look something like this. The water level at the upstream end has increased, while the water level at the downstream end is remaining where it is. So then I'll have some kind of a storage that looks like this. Okay, so this portion is the prism storage, and this portion is called the wedge. Okay, I'm sure you've seen. I hope you're familiar with the word wedge. Wedge is basically something that looks like this. Okay, sometimes for a door stopper you have something like this, right? When the door is, if you want to prevent the door from shutting, you just insert a wedge at the bottom of the door. This kind of shape is typically referred to as a wedge. Okay, so the storage in the channel is basically a combination of this prism storage and the wedge storage. Okay, so that is the fundamental understanding that I want you all to have. Okay, so then I'm saying that the storage of this channel is basically a combination of this prism storage and the wedge storage, naturally, right? So now the question is, how do we incorporate these two pieces of information into a method which allows us to understand this, the way the flood passes through the channel. Okay, so for that we have what is called the Muskingum method. Okay, and I'll be describing that. And I think we are over time. Okay, so we have just crossed the time limit. Okay, so we will meet today afternoon at 2 o'clock. So this is to make up for the lecture that we missed last week. So make sure all of you are present. I'm going to be explaining this Muskingum method in the afternoon lecture. Okay, and we'll probably try to solve a problem just like we did now, with the level 4 routing method. All right, thank you very much. Take care, and we will meet at 2 o'clock this afternoon. All right, so if you have any questions, just hang on until 2 o'clock. We'll answer them in the afternoon. All right, thank you very much. See you guys.